Earthquake magnitude is a measure of the size of an earthquake. When we experience an earthquake, we're experiencing shaking at our location. How much shaking we feel will depend on a lot of things, primarily on the size of the earthquake, but it'll also depend on things like how far we are from the earthquake, from the epicenter, how deep is the earthquake, how far is it from land surface, and other factors. And ultimately, it depends on how much energy is released by the earthquake. So how do we measure how big earthquakes are? A seismograph is a station that produces a record of the amount of shaking experienced at some distance from an earthquake. The paper record, this kind of squiggle graph that's produced by a seismograph, is called a seismogram. So in this picture, we see a simple seismogram that shows two of the types of seismic waves that are produced by earthquakes. Both of these that we're seeing are the body waves produced by an earthquake. So this is early time. We don't see a lot of motion of the ground, and then all of a sudden we start seeing a big shift, motion along the ground. That tells us that the earthquake has reached our seismograph station at this time. The first waves to reach the seismograph station are the P waves, and then the second are the other type of body waves called the S waves. And you see that the S waves produce greater ground motion, more displacement from zero. So when this magnitude scale was first developed by Charles Richter, his reasoning was that the size of an earthquake has to be proportional to the amount of shaking that is being felt at some distance from the earthquake. So he created this scale so that we could talk about how big earthquakes are and compare the size of earthquakes. And this Richter magnitude scale is the one that's most commonly used, although there has been updates to the Richter magnitude scale. There is now also moment magnitude scale, which is a little more accurate at describing very large earthquakes, like magnitude 8 or 9 and above earthquakes. But the idea behind both of them is the same. An earthquake magnitude scale is a logarithmic scale, and it determines the magnitude of the earthquake by measuring the amplitude of the largest ground motion produced on a seismograph that is 100 kilometers from the epicenter. And so if we're looking at this seismogram and we're seeing the largest displacement, the largest amplitude, amplitude is measured from midpoint to the top of the tallest wave, or midpoint to the bottom of the tallest wave. So that would be amplitude. So the larger the amplitude, the larger the magnitude of the earthquake. The larger, or another way to say that is, the larger the magnitude earthquake, the more ground motion it causes. So we can determine the magnitude of an earthquake by looking at this amplitude of the largest wave. And then we also have to take into account how far the seismograph station is from the epicenter. So over here we could plot the distance from the epicenter, and over here we would plot the amplitude of the largest wave. So in this case, it's a little bit over 20 millimeters. We plot that over here, and you draw a straight line from the distance to the amplitude on this particular type of scale, and it will give us the magnitude of the earthquake. The magnitude scale, as I said, is a logarithmic scale, and it ranges from 1 or 0 to the largest earthquake ever experienced, which is roughly, so far, 9.5 or so. So since it's a logarithmic scale, what that means is that for every single number increase in magnitude, for example in Richter magnitude, that means that the amount of motion experienced on the ground increases by a factor of 10. So for example, at some distance away from an earthquake of magnitude 6, if the amount of displacement experienced and recorded by the seismogram is 1 centimeter, then for an earthquake that happens at the same location but is 1 magnitude greater, the amount of ground motion experienced at the same seismograph station will be multiplied by 10. So instead of experiencing 1 centimeter of shaking, now we're experiencing 10 centimeters of shaking. And if there were another earthquake that would happen at the same epicenter, and it was 1 magnitude greater than the 7, so 2 magnitudes greater than a magnitude 6 earthquake, we would experience 10 times 10 the amount of shaking, or 100 centimeters of shaking. So decrease in magnitude works in the opposite direction. If a magnitude 6 earthquake produces 1 centimeter of ground shaking, then a magnitude 5 earthquake that happens at the same location will produce shaking at the same location that experienced 1 centimeter. It'll produce 10 times less, meaning 1 centimeter divided by 10, a tenth of a centimeter of shaking, just 1 millimeter of shaking. If the magnitude is 2 numbers less, magnitude 4, the same location, it will produce 10 times 10 less shaking, or 1 centimeter divided by 100. Just a single tenth, 1/10 of a millimeter of ground motion. To kind of get a visual idea of how this works, imagine that you are some distance away from an earthquake. You experience 1 centimeter of ground motion at your location, but then another earthquake happens that is 1 magnitude larger. You will experience 10 times that amount of ground motion, or 10 centimeters of shaking. So kind of going back to the beginning, if you experience, for example, 1 centimeter of ground motion from a, let's say, magnitude 5 earthquake at some distance away, a magnitude 4 earthquake will produce 1/10 that amount of motion, or just 1 millimeter of motion. So that tells us, that gives us a way to compare the amount of motion that we experience from an earthquake. But what we also care about is the total amount of energy released by an earthquake. Energy, when we typically experience energy in day-to-day life, we quantify the amount of energy by using units such as watts or calories. But when we're talking about the amount of energy released by an earthquake, we're talking about much larger amounts of energy. So one way to describe the amount of energy released by earthquakes is that you can compare them to the amount of energy released by atomic bombs, for example. And so how do we compare the amount of energy released by earthquakes of different magnitudes? Well, since it's a magnitude scale, there's a logarithmic scale, for every decrease or increase in magnitude, the amount of energy released is multiplied, but this time not by 10, but by 30 times. So for example, if there's a magnitude 6.3 earthquake, and let's say the amount of energy released by that particular earthquake is equivalent to the energy released by 500 atomic bombs, then a magnitude 7.3, 1 magnitude greater earthquake happens, that energy released by that earthquake would be 30 times the energy released by the magnitude 6.3 earthquake, or it would be roughly the amount of energy equivalent to the energy released by 15,000 atomic bombs. 2 magnitudes greater would release 500 times 30 times 30, or the amount of energy equivalent to that released by 450,000 atomic bombs. So in other words, a magnitude 8.3 earthquake releases 30 times 30, or 900 times more energy than a magnitude 6.3 earthquake. A magnitude 9.3 earthquake, which is a very large earthquake, releases 30 times 30 times 30, or 27,000 times more energy than a 6.3 magnitude earthquake. So again, if that 6.3 magnitude earthquake released as much energy as a 500 atomic bombs, then a 9.3 magnitude earthquake would release as much energy as equivalent to 13,500,000 atomic bombs. And so to go backwards in this, you would just take each amount of energy and divide it by 30, the number of times less.